Welcome to Introductory Chemistry with Dr. H. This is a quick video about some colligative properties, particularly vapor pressure lowering and boiling point elevation. Those two phenomena are examples of colligative properties, so I'm going to give you a quick introduction to colligative properties and then talk about vapor pressure lowering and Raouls Law and boiling point elevation and the Raouls boiling point elevation constant. So there are some properties of solutions that depend only on the number of particles that are dissolved in the solution. And so the important thing that means is, these properties are going to depend on some understanding of the concentration of that thing that's dissolved that relates to the number of particles of that thing that's dissolved, the solute that's dissolved. But really importantly, it really doesn't depend, these properties don't depend on the nature of what is dissolved. It's simply the number of particles, right? So these are really interesting properties and they're really important. So for an example, we're going to start by talking about vapor pressure lowering. And so if you imagine just water molecules, and so if you think about this left beaker having water molecules in them, in this left beaker, it's only water molecules, it's pure water, and we know that on the surface of that water, some of those molecules are going to have enough energy to pop out into the vapor phase, and those molecules bouncing around in the vapor phase cause vapor pressure, right? Molecules moving around in a vapor colliding with the walls of something are what cause pressure. And so there's a number of water molecules above that solution that cause the vapor pressure of water. Now imagine what would happen if you dissolved some non-volatile substance into that water. For example, sugar. Sugar is a molecular compound. It doesn't have any vapor pressure because its boiling point is so high there's no way you could give a glucose molecule enough energy to pop out of the solution. So if our glucose molecules are green or something, those glucose molecules are going to spread themselves around kind of evenly within the solution. But really importantly, along the surface of the solution, there are going to be several locations on the surface where a water can no longer occupy that part of the surface. And so if a water molecule can't occupy that part of the surface, there's no chance that a water molecule is going to both have enough energy and have the access to the surface to pop out. So you can think about it kind of like glucose molecules blocking some of the spots that some waters might have a chance to escape from. So what you see is that the vapor pressure above a solution of a non-volatile substrate tends to go down. It goes down because some of the locations on the surface are blocked by that non-volatile substrate. And so what you see is fewer molecules making it into the vapor phase, and if there are fewer molecules there, then that's going to create a smaller pressure. And so that's why it's vapor pressure lowering. So colligative properties, though, in general, are just these properties that depend on the number of particles. And all of the arguments we make about colligative properties are something like the argument I just made. When you have an alternative molecule filling the space of the solvent molecule, that's going to change the properties of that solvent, right? And so it has to do with freezing point, we'll talk about that later, and boiling point and vapor pressure, which is what we're focusing on right now. So there are a number of concentration units that describe colligative properties, and we've talked already about mole fraction as one particular concentration unit that describes the relationship between a solvent, the moles of a solvent, and the moles of the thing that's dissolved within it. As it turns out, vapor pressure is related by Raouls Law. So let's first imagine we have a solution like I described on the first slide, where we have a non-volatile solute in a solution. So let's walk through Raouls Law. The total pressure of a solution is going to be equal to the vapor pressure of that pure solvent, P1. I'm going to call P1 the vapor pressure of the solvent. If it were pure, times the mole fraction of that solvent. So if it's only solvent, that number is going to be 1. Mole fraction is going to be 1 because it's only solvent. And so the pressure above it is going to be the pressure of the pure stuff times 1. That makes sense. Now, if you start dissolving a non-volatile substrate in there, the mole fraction is going to go down. So the pressure above that solution is going to decrease as x1 goes down. And importantly, when we're talking about a non-volatile substrate, the vapor pressure of a non-volatile substrate is 0. So that means this second term of Raouls' law is 0. So there's no contribution to the pressure from the non-volatile substrate. That's why we call it non-volatile. So So this equation, Raoul's law, simplifies when you have a non-volatile substrate, a substrate with very high boiling point, right? And to just this sort of left term of this equation. So the total pressure of the solution is going to equal the pressure of the solvent times its mole fraction. And just to remind you, the mole fraction is equal to the moles of one, which would be the solvent in this case, divided by the total moles. And so that's going to be the moles of one plus the moles of whatever substrate are there, right? So that fraction is all of a sudden going to be less than one, and so the vapor pressure is going to decrease. We already talked about that, and the reason why, right, is those non-volatile substrates are taking up some of those spots on the top. Okay, so that's Raoul's law for a non-volatile solute. Now, if you have a volatile solute, that second term comes into play. All of a sudden, these green molecules also can make it into the vapor phase, and how likely they are to make it into their vapor phase depends on their own vapor pressure, P2. So P2 naught means the vapor pressure of pure volatile substrate 2. Okay, and so the total vapor pressure is just the sum of the vapor pressure of the original solvent times its mole fraction, plus the vapor pressure of the volatile solute times the mole fraction of that volatile solute. So the vapor x1 plus x2 have to add up to 1. They're just fractions, right? So that sums up to the total pressure. And I don't think I have to write out sort of the definition of the mole fraction of 2 because it's the same type of equation as this one. x1, the mole fraction of 1 is the moles of 1 divided by the total. x2 would just be the moles of 2 divided by the total. And so now both solute and solvent are contributing to the vapor pressure because all of those particles are making it out into the vapor. Now, the thing that I just described kind of makes sense. And so we can kind of do a quick plot of what that would look like. So if we had only x1, only the solvent, and I call this the pressure here, I'm just going to call this P01 over here. If we had a mole fraction of 1, that would be the pressure because there would be none of the volatile solute. And on the other side of this equation, I'm saying the mole fraction is completely 2. So the mole fraction of x1 is 0, the mole fraction of 2 is 1. So you know, the pressure as you sort of go across there, as you slowly introduce more of that volatile solute, would be kind of a straight line across there. Sometimes, in some cases, it is a straight line, meaning this equation holds perfectly. That only happens when we have what is known as an ideal solution. So an ideal solution is one where the intermolecular forces between solute 1 and itself are the same as the intermolecular forces between the solvent and the solute. So that means those molecules are going to be very similar in nature. You know, there are very few examples of really ideal solutions. One example, which is one we work with in organic chemistry, is benzene and toluene. Those two have very different boiling points. They differ by about 30 degrees Celsius. And when you mix them together, they generate a Raoul's law line that's very much straight across that whole temperature range, and it goes pretty much from the pressure of benzene up to the pressure of toluene as you change the mole fraction of each. And that's because those molecules are so similar. Their intermolecular forces are really similar. A benzene-benzene intermolecular force is really similar to a benzene-toluene intermolecular force, which is really similar to a toluene-toluene intermolecular force. So that's known as an ideal solution. So in some cases, the intermolecular forces between the solute and the solvent are stronger. When those intermolecular forces between the solute and the solute are stronger, when they're mixed together, those stronger intermolecular forces in the mixture actually make a negative deviation to Raoul's law. So I'm going to kind of like use green to so the intermolecular forces between the solute and the solvent being stronger, you sort of get a negative deviation from Raoul's law. Now it ends at the same points because that means that's just pure solvent on the ends. So that would be an example of stronger intermolecular forces between the solute and the solvent. There are also examples, of course, where the intermolecular forces between the solute and the solvent are weaker. And so let's pick another color like pink, for example. When the intermolecular forces are weaker, when those two are mixed like in a 50-50 proportion, the net intermolecular forces holding molecules in the solution go down because that's a weaker intermolecular force. So see a positive deviation to Raoul's law. There's more pressure above the solution than you would predict because the intermolecular forces are weaker. So, we often treat solutions as if they're ideal, but we have to be aware when we observe a positive or negative deviation what that means about intermolecular forces. All right. So boiling point elevation. This is another colligative property that's very much related to the vapor pressure one, which is why I included it in this little video. We already have a sense that the vapor pressure above a solution of a non-volatile substrate, so we're talking about non-volatile solute in this case again, the vapor pressure above it's going to be lower. What that means is in order to get the vapor pressure above the solution to be equal to the atmospheric pressure or the pressure in the environment, we're going to have to heat that solution hotter, right? So that's the definition of a boiling point, is the temperature at which the vapor pressure above the solution is equal to the pressure in the environment. So because there's a lower pressure above a solution with a solute, we have to heat it hotter. That difference in temperature is called the boiling point elevation, delta temperature boiling. And the way we understand that is using a different one of the concentration units, the concentration molality. There are big tables of what are called molal boiling point elevation constants. And that constant is for the solvent. So say, for example, this is water. You could look up the molal boiling point elevation constant for water. And what that says is, if you had a concentration of 1 molal of anything, right, it could even be different things that are non-volatile, a total concentration of 1 molal, and what you would observe is that the boiling temperature goes up by about a half a degree, by 0.52 degrees. So every time you increase the concentration of the solute, you have to heat it a little bit hotter to get the thing to boil. And so we can calculate that difference by multiplying this molal, boiling point elevation constant, times the molality of the total concentration of non-volatile solutes that are dissolved. And I keep saying it because it's kind of important. You don't have to only have one kind of substrate. It's that molality is the sum. So you could have like some pink, if you will, non-volatile molecules, and you could have some green non-volatile molecules. It's the sum of all of them, because really it just matters the number of particles, not their identities. It's the total number of particles that are there. And here I'm focusing again on non-volatile ones. These are ones that don't have their own vapor pressure, and they're not going to add to the pressure above the solution to make it boil earlier. Non-volatile substrates elevate the boiling point. Okay, so I think I've discussed everything related to these in terms of their concepts, and these are the equations that you need. So I hope you found this video useful.